This is part 2 of our deep dive course on work orchestration for agentic engineering, where we're going to cover an analytical taxonomy of orchestration systems. We'll discuss the difference between context-based orchestration and external execution orchestration, persistent workspace and programmatic orchestration, and workspace orchestration.
Welcome to this lesson on one of the most crucial concepts in today's orchestration landscape, context-based versus external execution orchestration. At its core, we are answering one simple but powerful question: where does your coordinating logic actually live? In this overview, we will break down both approaches and explore the core trade-offs you need to balance, specifically flexibility versus control and persistent versus fresh context. From there, we will map these concepts directly to real-world tools, explore the middle ground between the two extremes, and uncover exactly why this distinction matters for your own builds. By the end of this module, you will walk away with the exact key takeaways needed to confidently choose the right architecture for your next system. Let's dive in. Let's dive into our first category, context-based orchestration. In this approach, coordination happens primarily through persistent context right inside the harness. Instead of a heavy external controller pulling the strings, we shape the agent's informational environment. This context can be made up of many different elements, including specific skills, plugins, initial instructions, /commands, memory files, research, overarching rules, repository artifacts, and project conventions. A really useful way to frame this category is to ask yourself a guiding question. Does the system achieve better behavior by loading better context and better flows directly into the agent itself? If the answer is yes, you are looking at context-based orchestration. So what does this actually look like in practice? The agent stays inside its normal working environment, but that environment has been carefully curated. The system might equip the harness with named skills for planning, implementation, or review. It might provide memory files that preserve the exact state of the project, or establish clear conventions for where plans and summaries should be stored. It could supply reusable research artifacts, or set repository-level rules that help the agent behave much more consistently. The orchestration here is very real, but it is expressed through the environment rather than through a heavy external manager. You will see this approach in several familiar setups from our course material. The clearest examples include setups like Obra Superpowers, the Get Shit Done framework, and various Claude Code, Codex, and open code environments that rely heavily on injected skills and conventions. You will also see elements of this in the Oh My Open Agent approach. There are several practical advantages to context-based orchestration. First, it is generally easier to adopt. Teams can improve a harness incrementally just by adding better skills, rules, and project artifacts over time. Second, the workflow feels natural. The user stays in a familiar environment instead of having to jump out to a separate orchestration layer for every single step. Third, it requires less external infrastructure. You often do not need an elaborate runner, scheduler, or loop manager just to see a meaningful improvement in performance. And fourth, it makes great use of whatever native features the harness already supports. This might include tools, hooks, subagents, /commands, repository memory, or internal task flows. However, this approach does have real limitations that you need to be aware of. For one, you are highly dependent on the harness. The quality of your results will rely heavily on how that specific harness behaves and what features it actually exposes. Another issue is that rules may be applied inconsistently. When you rely entirely on context and conventions, the agent might follow them unevenly, especially during long, complex, or messy tasks. Furthermore, governance becomes much harder at longer horizons. As the work becomes more concurrent or organizationally complex, it is difficult to govern the entire process through context alone. Finally, there is a serious risk of context rot. If important state information is not externalized well, the system can suffer from drift, compression, noise accumulation, or a degraded sense of continuity over time. Now let's explore external execution orchestration. In this approach, the coordination happens outside the agent's harness. Instead of relying on a persistent internal memory to keep things on track, an external layer takes charge. Think of this external layer as a manager. It decides exactly when to invoke the agent, what input to provide, which files or artifacts to target, what needs to be validated, whether to retry a task, and when to launch a fresh iteration. A useful guiding question here is, does the system achieve better behavior by making the agent work in controlled iterations, governed by an outside layer? In practice, this usually takes the form of a script, a loop, or a wrapper acting as the main coordinator. This outer shell repeatedly launches fresh agent sessions, inspects the outputs, updates the external state, and decides what happens next. This cleanly separates the agent's local work for a single iteration from the overarching control logic that runs the broader process. Some of the closest examples of this include Ralph Wiggum and its loop-based variants, or custom automation wrappers built around tools like Claude Code, Codex, AMP, Goose, Cursor, or OpenCode. There are several reasons why this orchestration style is so attractive. First, it provides fresh context for every iteration. Starting a new session avoids carrying the dead weight of a long, noisy conversational history, which reduces drift and forces a clean re-entry into the task. Second, it offers much better control over retries and boundaries. Because the outer layer owns the loop, you can enforce strict stopping conditions and retry limits. Third, it simplifies validation. You can insert explicit checkpoints between iterations, pausing to verify the work before continuing. And fourth, it offers great portability. If an agent exposes enough of a command line interface, you can often adapt that same outer loop pattern across multiple different agent harnesses. However, there are a few trade-offs to keep in mind. First, this approach relies heavily on external file contracts. Because the external loop manages the state, it depends on saved artifacts, structured outputs, or progress files. If those files are poorly structured or inconsistent, the system becomes fragile. Second, it often lacks a native product feel. The user experience can feel a bit more like operating a scripted mechanical workflow rather than interacting with a seamless integrated agent. And finally, there is simply more surrounding infrastructure to deal with. Someone has to build, maintain, and troubleshoot that outer control layer, including all of the state handling, relaunch logic, and validation steps. Let's explore the core trade-off at the heart of these approaches: flexibility versus control. This distinction actually maps to one of the most central tensions in the field right now. On one hand, context-based systems are generally much easier to adopt. On the other hand, external execution systems typically provide a lot more control and repeatability. Now, it is important to understand that this does not mean one approach is inherently superior to the other. It simply means they optimize for entirely different things. Let's break that down. Context-based systems optimize for a seamless native harness experience. They come with a much lower setup cost, give you a great deal of flexibility right inside the active session, and make better use of harness native capabilities. If you want to get up and running quickly and dynamically, this is often the way to go. In contrast, external execution systems optimize for structure and predictability. They excel at controlled iteration and maintaining contextual freshness. Because the execution is handled externally, you gain the ability to perform explicit validation and set bounded retries. This approach also creates a much better separation between the system's local reasoning and the broader outer workflow. Ultimately, this fundamental tension is one of the main reasons the field has not converged on a single winner. The right choice simply depends on what your specific application needs to prioritize. Now let's explore a fascinating tension at the heart of these systems: the trade-off between persistent context and fresh context. Think of it as the balance between holding on to a conversation and hanging up the phone to start over. When we keep a context alive, we save a lot of effort. The system doesn't have to rebuild or recompose its understanding from scratch. Context-based systems lean heavily into this. They try to preserve a continuous, unbroken environment, which is incredibly useful when subtle details matter and the system has a reliable way to maintain that ongoing state. But there is a catch. The longer a context stays active, the more prone it is to wandering off track, a problem known as drift. Because of this, external execution systems take the exact opposite bet. Rather than trying to keep the memory alive indefinitely, they deliberately hit the reset button on the local session. To avoid losing progress, they rely on external memory. They reintroduce only the specific state that matters by reading from external artifacts, like saved files, structured plans, or concise summaries. This gives rise to a really powerful and perhaps counterintuitive idea: controlled forgetting can actually be a feature. Starting a fresh session is not a loss. In many systems, injecting a little bit of partial amnesia is exactly what prevents context rot. By clearing out the conversational clutter and reloading only the essentials, the system stays sharp and focused. This strategy of deliberate resetting is actually one of the most valuable lessons we can learn from Ralph-style operational loops. Sometimes the best way to maintain clarity is to know exactly when to forget. Now let's talk about how these concepts map to the real tools you will actually encounter. Throughout this course, we use this distinction between context-based and external orchestration as a foundational part of a broader taxonomy. It helps us easily categorize how different systems operate under the hood. First up is context-based orchestration. If you are using tools like Obra Superpowers, Get Shit Done, or certain parts of OhmyOpenAgent, you are primarily working in this space. You will also recognize this pattern in harness setups that rely heavily on built-in skills, custom commands, memory files, and internal conventions to guide the AI's behavior from within its own environment. On the flip side, we have external execution orchestration. This approach is closest to tools like Ralph Wiggum. It is characterized by loop-based wrappers and external automation patterns. Instead of managing everything from the inside, these systems sit on the outside, repeatedly invoking and managing the AI harnesses externally. Now, it is important to keep in mind that the tech landscape is rarely black and white. This does not mean every single tool will fit perfectly into just one of these buckets. In practice, many real-world systems actually blend both of these patterns to get the job done. But by understanding these two core approaches, you will have a much easier time breaking down, evaluating, and mastering whatever tools you decide to use. In practice, the strongest systems don't force you to choose just one path. Instead, they find the middle ground and mix the two approaches. Why does this happen? Simply put, each side naturally compensates for the other's weaknesses. For instance, systems like GSD and superpowers show us that context-based orchestration becomes significantly stronger when it produces persistent, lasting artifacts, rather than just relying on the temporary state of a live session. On the other hand, systems like Ralph prove that external orchestration works best when those external artifacts are carefully designed to preserve exactly the right state across multiple iterations. This is why the boundary between these two categories is a highly useful concept for learning, but in actual operation, that boundary is incredibly porous. So, what does a practical hybrid pattern look like? In a real-world system, you might rely on strong internal skills, established conventions, and memory files right inside the main harness. But then, you take that entire harness and wrap it in an external loop. This outside loop acts as a supervisor, controlling retries, running validation checks, and managing relaunch behavior. This specific pattern pops up all the time, and for good reason. It is highly effective because it perfectly combines the smooth fluency of context-based coordination with the strict reliability and discipline of external control. So why does this distinction actually matter? It is because the choice between these two orchestration styles leads to very different practical realities when you are building and using these systems. Let's break down these differences. First, think about where the coordinating brain of the operation lives. In one style, that brain lives right inside the AI harness, relying on the model's context and built-in artifacts to make decisions. In the other style, the brain lives outside the harness, controlled by a traditional script or a programmatic loop. Because of this, the type of memory that dominates the system changes entirely. When orchestration happens inside the harness, the system relies heavily on built-in skills, system prompts, and internal repository memory. But when orchestration happens outside, the system depends heavily on external files, explicit state artifacts, and progress trackers managed by the external loop. This naturally leads to two very different user experiences. The internal style feels like a more native, integrated harness experience, where you are working directly with the AI in its own environment. The external style, on the other hand, creates a more explicit control workflow, where you are actively managing and monitoring repeated runs from the outside. And of course, each style has its own unique ways of failing. With internal orchestration, your biggest risks are context degradation and the AI inconsistently applying rules as the conversation grows. With external orchestration, the danger shifts to brittle file contracts, where a tiny change in an output format breaks the whole pipeline, along with the sheer weight of maintaining that heavier outer infrastructure. Ultimately, these are not small differences. The orchestration style you choose fundamentally shapes how the system feels to the user, how effectively it can scale, and perhaps most importantly, how much human micromanagement it will still need to get the job done right. As we bring this section to a close, let's focus on the key takeaway. One of the most fundamental design distinctions in agentic engineering is the contrast between context-based orchestration and external execution orchestration. Think of it this way. Context-based orchestration improves an agent's behavior by working directly within its immediate environment. It focuses on loading better, richer context and smoother operational flows straight into the prompt harness itself. External execution orchestration takes a completely different route. It improves behavior by placing the agent inside a controlled outer loop. This outer system acts as a supervisor, managing fresh iterations, validating the agent's work, and handling retries if something fails. At the end of the day, both approaches are trying to solve the exact same problem, getting an AI to successfully complete complex, long-horizon, autonomous tasks reliably. They simply place the main coordinating logic in different locations. Why does this distinction matter so much? Because it helps you clearly see where your system's real control surface lives. Are you steering the agent from within its own working memory, or are you guiding it using a system wrapped around it? Grasping this concept prepares you for the next layers in our taxonomy, where we will watch orchestration move even further outward. Next, we will explore how this control expands into persistent workspace managers, deep integrations with software development kits and protocols, and finally, complete end-to-end work systems. Welcome to this lesson on persistent workspaces and programmatic orchestration. As agentic engineering matures, we are seeing a fascinating shift. Orchestration is moving outward. In this overview, we will map out exactly how and why this evolution happens. We will explore the mechanics of persistent workspaces, learning why they are so much more than just simple memory. Then we will dive into programmatic orchestration. You will discover how SDKs, protocols, and embeddable runtimes go far beyond basic function calling to enable complex, long-running, and highly iterative work. Finally, we will see how these two powerful layers reinforce each other and exactly where they fit into the broader AI taxonomy. This is the exciting frontier where AI stops just generating text and starts actively driving real software systems. Let's dive in. Context-based orchestration can already accomplish a great deal. A well-configured harness, one equipped with strong skills, repository memory, and solid project artifacts, can drive surprisingly capable behavior. But eventually, you hit a wall. There are hard limits to how much you can coordinate purely inside a single live session. As tasks grow in duration and complexity, the demands on the system change. You start needing continuity across multiple iterations and an explicit state that lives completely outside the chat window. You need cleaner ways to pause and re-enter the work, along with stronger, more reliable control over retries and handoffs between different parts of a system. Furthermore, these complex tasks require deep integration with host applications and existing workflows, plus a foolproof way to preserve work even when the active session comes to an end. Addressing these growing needs is exactly why orchestration has to move outward. It paves the way for the next level of complexity, which is where persistent workspace orchestration and programmatic orchestration come in. Let's move on to our next key concept, persistent workspace orchestration. Simply put, a persistent workspace is an environment where work survives beyond a single run of an AI agent. This is incredibly important because long horizon engineering tasks usually cannot be treated as a completely fresh start every single time. To be effective, the system needs a dedicated space where artifacts, partial progress, repository state, logs, and other work products can naturally accumulate and remain available for later iterations. So, what exactly does a persistent workspace contain? It can hold a wide variety of project elements. This includes checked out code, working branches, generated files, and system logs. It is also where the agent stores plans, notes, state documents, and cached research. You will even find test results and partial implementations left over from previous runs. While the exact technical setup might vary from system to system, the guiding principle is always the same. The system must have a durable, reliable place to resume its work. To understand why this matters, imagine running a system without one. Without a persistent workspace, the system faces heavy, repeated recomposition costs. Every time it starts a new step, it has to waste time rediscovering its prior state. It risks losing hard-earned partial progress, and it is forced to rely heavily on summaries or reconstructed context just to figure out what to do next. Furthermore, without a lasting record, it becomes incredibly difficult for developers to look back and inspect what actually happened during a run. A persistent workspace fundamentally changes this dynamic. By preserving the environment, it gives the orchestration layer something concrete and tangible to return to, making complex, multi-step engineering workflows much more transparent, efficient, and reliable. It is tempting to think of persistent workspaces as just another form of long-term memory, but that framing does not quite capture the whole picture. The easiest way to think about the difference is this. Memory is about what the system knows, while a workspace is about where the work actually lives. A persistent workspace goes beyond preserving abstract knowledge. It preserves the actual operational surface of the task. This means holding on to the current state of your code, your active working files, and the specific artifacts you are modifying. It also preserves the state of your verification outputs and the exact environment needed so you can seamlessly pick up the next step right where you left off. This is incredibly important in engineering work. In complex projects, continuity usually depends on having access to these material artifacts and active environments, rather than just relying on conversational recall. So it helps to make a clear distinction here. A system might preserve its context through things like summaries, state files, or memory artifacts, but it preserves its workspace state by maintaining a durable working environment. Ultimately, to be truly effective, strong systems need both. Let's move on to our fourth category, persistent workspace managers. Sometimes orchestration systems need to go a step further than simple data persistence. They act more like actual workspace managers. But what does that really mean? Well, a persistent workspace manager doesn't just store files. It actively coordinates the entire lifecycle of a work environment. It can create a brand new workspace for a specific task, or smartly reuse an existing one. It can isolate work based on a specific issue or a code branch, preserve the intermediate state of a project, and seamlessly hand that workspace from one iteration to the next. It also makes it much easier for a human operator to step in, inspect what is going on, or resume paused work. This is a completely different level of orchestration than simply attaching a memory file to an active session. We treat this as a distinct orchestration category because it moves the coordination layer outside the immediate live context of the agent, but it doesn't go all the way up to a full high-level issue tracking system. It sits perfectly in the middle. At this level, the system is no longer just asking what should the agent know right now. Instead, it is asking larger logistical questions. Where should this work continue? Which specific environment owns this task? And what state needs to stick around across retries or handoffs? That is what makes persistent workspace orchestration its own highly important category. To help visualize this, a system called Gastown is often used as a reference point for this style of thinking. Now, the goal isn't to copy the exact way Gastown is built. The real conceptual lesson here is about long horizon autonomous work. That kind of work becomes incredibly powerful when it has a dedicated place to persist, a reliable place to resume from, and a stable environment where multiple iterations can build on actual existing state rather than having to reconstruct everything from scratch every single time. Now let's look at our fifth concept, programmatic orchestration. If our previous topic, persistent workspace orchestration, was all about where work lives, programmatic orchestration is about how software systems actually control that work. This type of orchestration happens when agent harnesses are embedded, invoked, or coordinated directly by other software. Rather than relying on manual human inputs, the system manages the agent through standard technical bridges. This is done using SDKs, APIs, communication protocols, embeddable servers, or broader programmatic host systems. The key takeaway here is the fundamental shift in the agent's role. At this point, the agent is no longer just a standalone tool that a user interacts with directly. Instead, it transforms into a programmable component, operating behind the scenes as a seamless, integrated part of a much larger application architecture. Let's talk about what programmatic orchestration actually enables, because it opens up some incredibly powerful capabilities for our systems. There are 5 major benefits here. First, agent harnesses become embeddable. Instead of treating the harness as a standalone user interface that people have to open up separately, your own host application can seamlessly launch and control an agentic session right behind the scenes. Because of this, we get our second benefit. Execution can be deeply integrated into your existing workflows. You can trigger an agent from almost anywhere. That might be a button in your main product user interface, an automated backend service, or a complex project workflow. You could even kick off an agent from a team chat interface, a customer ticketing system, or directly inside a development environment. Third, programmatic orchestration allows us to surface the intermediate state of an agent's work. Instead of a black box where you just wait for a final answer, the host system can constantly receive and display real-time information. This includes live events, streaming updates, and visibility into the exact tool calls the agent is making. It also lets you monitor pending approvals, final execution results, and crucially, any failure states as soon as they happen. And because we can see what the agent is doing in real time, we arrive at our fourth benefit. It is much easier to keep humans in the loop. You can program the system to safely pause work at meaningful checkpoints, allowing a person to step in, review the progress, approve a sensitive action, or redirect the agent if it is drifting off course. Finally, all of these capabilities lead to a major architectural shift. The agent harness is no longer the entire product. Instead, it becomes just one highly capable component functioning within a much larger control plane. It transforms the agent from an isolated tool into a core piece of a fully composed intelligent system. Let's explore one of the major ways programmatic orchestration happens today, through software development kits, or SDKs. The landscape currently features several important examples. You might be familiar with the Claude Agent SDK or the OpenAI Agents SDK. There is also the Codex SDK, the OpenHands Software Agent SDK, and the OpenCode SDK. While these are not identical in their design or scope, they all serve a very similar, crucial role. They provide a programmatic surface that allows a host system to seamlessly coordinate the behavior of an AI harness. So, what exactly changes once a harness is equipped with an SDK? The short answer is that the host system can now do much more than simply prompt the AI and wait. It gains deep programmatic control. Through the SDK, the host system can launch and configure the agent, provide it with specific tools, and stream real-time updates. It can capture generated artifacts, manage approval workflows, react dynamically to intermediate results, and integrate the agent directly into the logic of a larger product. Essentially, this moves orchestration squarely into the territory of traditional software engineering. The agent is no longer a standalone tool, it becomes a fully controllable piece of your application stack. This shift is incredibly important. SDK-based orchestration is one of the clearest signs that the field is moving rapidly beyond the concept of AI as just a chat interface, and toward a future where AI acts as a powerful programmable subsystem. Now let's talk about programmatic orchestration and clear up a common misconception. It is not just function calling. While letting an AI model emit a structured tool, call is definitely an important piece of the story, it is far from the whole thing. programmatic orchestration is much broader. Think of it as the comprehensive system that manages how work actually gets done. It involves lifecycle management to oversee the start-to-finish process of your tasks and state passing to ensure the right data moves smoothly from one step to the next. It also encompasses complex operations like human-in-the-loop approval flows and real-time event streaming. It is about seamlessly embedding the AI harness into your other existing systems and intelligently routing tasks between different execution units. Crucially, it provides host-driven control. This means your system, rather than just the model, ultimately dictates exactly when and how the work is executed. Because of all these critical responsibilities, this goes far beyond a simple API feature. It is a foundational architecture, which is exactly why it belongs squarely in our broader discussion about orchestration. Let's explore protocols and embeddable runtimes. Programmatic orchestration goes beyond sending simple one-off commands. It involves deeper runtime and protocol layers that allow one system to control another in a highly structured and persistent way. One of the most important examples we discuss in this course is the Codex app server. It is vital to understand that its true significance is not that it is just another software development kit. Rather, it is a breakthrough because it exposes Codex as a fully embeddable runtime. In practice, this means it comes equipped with persistent sessions, two-way communication, real-time event streaming, approval workflows, and the ability to be controlled directly by an outside application. Because of these powerful features, a larger orchestration layer can treat Codex not simply as a conversational chat tool, but as a dynamic engine operating quietly inside a much broader system. Conceptually, this is a major turning point. This is the exact moment where the AI harness stops behaving like a standalone interface and transforms into foundational infrastructure. That shift matters enormously as it paves the way for the entire future of agentic engineering. Now let's explore how persistent workspaces and programmatic orchestration reinforce each other. While these are two fundamentally different layers of orchestration, their real power is unleashed when they work together. Think of persistent workspaces as your foundation for continuity. They give the work a concrete place to live. They make the state of any task fully inspectable, and they allow processes to be easily resumed across time. On the other hand, programmatic orchestration acts as your control center. It handles the software-level coordination. This layer gives you routing, embedding into your existing systems, host-driven integration, and the logic needed for managing approvals. When you combine the two, you unlock the ability to build incredibly robust systems. Because of the persistent workspace, your work survives well beyond a single run, allowing the system to support much longer workflows without having to rely on one continuous session. At the same time, programmatic orchestration ensures that this entire environment is controlled by real software. This means that state can always be resumed cleanly, and humans can easily step in to intervene at exactly the right, meaningful moments. Ultimately, combining these two layers represents one of the clearest transitions you can make from simple agent use toward true operational autonomy. Let's take a step back and see how these layers fit into our broader course taxonomy. Earlier, we established a distinction between two foundational types of orchestration. First, there was context-based orchestration. This approach focuses on improving behavior from inside the harness by providing better, richer informational environments. After that, we explored external execution orchestration, which steps outside the immediate environment to improve behavior using outer loops and fresh controlled iterations. Now, persistent workspace orchestration and programmatic orchestration take us to the next level by pushing the control surface even further outward. Persistent workspace orchestration provides a durable operational environment for the work. Instead of resetting, it gives the system a continuous space that persists across time. Programmatic orchestration pushes the boundary even further. It allows entirely separate host systems to control and integrate harness behavior using raw code, SDKs, and communication protocols. When you look at these four stages together, a clear trend emerges. We start on the inside with context, step out to external loops, expand into persistent environments, and finally hand over control to external host systems entirely. This progressive, outward movement of the control surface is a defining pattern in the field, and recognizing it will help you understand how complex systems are ultimately woven together. Let's wrap up with our core takeaway. As agentic systems mature, orchestration increasingly expands beyond a simple live session. In this expansion, two specific layers become incredibly important. The first is persistent workspace orchestration. This is what gives long-horizon work a durable environment, a dedicated space where an agent can safely operate and maintain context over extended periods of time. The second is programmatic orchestration, which allows your existing software systems to directly embed, control, and coordinate these agents behind the scenes. These layers matter because achieving true autonomy is not solely an AI reasoning problem. It is fundamentally a systems problem. Think about what an advanced agent actually needs to succeed in a real-world workflow. It might need a dedicated place to pause and continue its work later. It needs a host application to drive it, a defined protocol for interaction, and a clear path for human approval. It also requires a programmable control layer and the ability to create durable artifacts like files or data that survive long after a single run finishes. Once these requirements become a priority, you have crossed a major threshold. Your architecture has moved far beyond simple prompting and well beyond single-session agent use. You are now building and managing a genuine orchestration system. Welcome to our overview of work system orchestration, the highest layer in our course taxonomy. In this lesson, we are going to explore a massive shift in how we work with AI. Instead of managing individual prompts or agent sessions, you'll learn how to orchestrate the work itself. We will guide you through what makes this layer unique, exactly what it coordinates, and why it emerges. You'll see how everyday items like tickets and workspaces become active control surfaces, and how explicit workflows, reviews, and retries bring everything together. Finally, we'll examine how this connects to the lower layers and look at a clear real-world example using Symphony. Get ready to fundamentally change how you approach agentic engineering as you step up to manage the entire work system. Let's dive in. By now we know that a harness can already do useful work. We know that adding skills can improve the behavior inside that harness and that external loops can relaunch fresh iterations. We also have workspace managers to preserve a durable working state, along with SDKs and protocols that embed these harnesses inside much larger applications. All of these pieces are incredibly valuable. Work system orchestration builds on all of that foundation, but it moves us up one more level. So what exactly makes this level different? It comes down to a fundamental shift in how we interact with the system. At this stage, the main unit of interaction is no longer the prompt. It is no longer mainly the session either. Instead, the unit of interaction becomes the ticket, the issue, or the work item. What this really means is that the system is now coordinating the entire lifecycle of the work itself, rather than just coordinating a back and forth conversation. You are stepping away from a chat interface and stepping into task management and completion. To figure out if you are at this level, there is a very useful guiding question you can ask yourself. Simply ask, does the human operator interact with work rather than interacting with prompts? If the answer is yes, then your system has successfully moved into work system orchestration. Let's explore what this layer actually coordinates. At its core, work system orchestration treats work as a persistent, operational object with a clearly defined lifecycle. Think about the entire journey of a task. This lifecycle includes the initial creation of a ticket, assigning a dedicated workspace, and routing the job to a harness or an agent runner. But it also manages the ongoing reality of getting things done. That means handling iterative execution, stepping in with retries if there is a failure, running test and review steps, updating status transitions, and finally, safely landing the completed changes. This comprehensive approach is exactly why we define work orchestration as a much higher layer than simply orchestrating a single isolated session. It doesn't just manage a brief interaction, it coordinates the entire lifespan of the work as one cohesive operational unit. So, what exactly goes into one of these units? Typically, a work unit ties together several different elements to keep everything organized. It involves the tracking ticket or issue, an isolated workspace, and a specific branch or work tree. It also includes the state files or progress artifacts that remember exactly where the task left off, along with test and review results, necessary approval points, and that final merge or landing step. To put it simply, at this layer, the system's perspective fundamentally shifts. It is no longer just asking, what should the agent do next? Instead, it is asking a much broader, more strategic question. What is the current status of this overall work item, and what needs to happen to it right now? So why does this new orchestration layer emerge in the first place? It really comes down to hitting the scaling limits of lower-level orchestration. Think about how we typically interact with AI. A person can easily guide one or two agent sessions directly. With some discipline, you might even be able to juggle a few more. But when you get into long-horizon engineering work, session-by-session control quickly becomes incredibly inefficient. You suddenly find yourself with way too many tasks to manage manually, and you are wasting time reloading context by hand for every new session. There are just too many retries, too many validations, and far too many moving parts scattered across different branches, files, and code reviews. On top of that, you need visibility across multiple concurrent efforts, which is nearly impossible to maintain by yourself. When you hit this wall, the problem is no longer just about the quality of the AI agent. It becomes a fundamental work management problem. Because of this, the role of the human operator has to change. You transition from being a chat pilot, steering the AI step by step, to becoming a work manager. In this new role, your focus shifts to the bigger picture. You are now the one who defines which work items actually matter and how the overall workflow should behave. You determine exactly where human approval belongs in the process and what criteria must be met for a task to be considered done. You also set the rules for what should happen when an execution fails and how code reviews and final integrations are handled. Ultimately, this is a macro management shift, and it sits right at the very heart of work system orchestration. Let's move on to the next major concept in this orchestration style: how tickets and issues transform into active control surfaces. Traditionally, we might think of a ticket as passive documentation, just a simple record of something to do. But here, they become the active control centers that actually drive autonomous work. Think of the work item as a comprehensive living briefing package. It doesn't just state the problem, it carries the boundaries of the task, the priority level, and the specific acceptance criteria. It holds the real-time status, links to relevant artifacts, and any human feedback or comments. It even maintains direct connections to the specific workspaces and code branches being used. Why does this matter? When the work item becomes the absolute center of coordination, your system gains a highly stable and inspectable representation of progress. This is a massive upgrade from trying to piece together what happened from a long, messy conversation transcript. By centralizing everything into an active ticket, it becomes incredibly easy to answer vital questions. At a glance, you know exactly what is being worked on, what has already happened, and what might have failed. You can immediately see what needs human review and whether a task is blocked or ready to move forward. Ultimately, treating tickets as active control surfaces brings these autonomous systems much closer to the way real, high-functioning engineering organizations already coordinate their work today. Now let's look at why workspaces are a core part of this layer. When we talk about work system orchestration, it almost always relies on isolated workspaces. Think of it this way. Each issue or ticket is assigned its very own working environment. By doing this, the progress the system makes becomes durable, it becomes easy to inspect, and it is far less likely to accidentally interfere with other ongoing tasks. But why do these issue-specific workspaces matter so much? For one, they support true continuity. If a task takes multiple steps or runs, the environment remembers exactly where it left off. This also allows for much cleaner retries if a step happens to fail. Because everything is completely isolated by the specific work item, the system can safely execute multiple tasks at the exact same time without them crossing wires. Plus, a dedicated environment makes it incredibly simple for you to look in and check on the progress of any given ticket. This concept is a key reason why we treat work system orchestration as something entirely distinct from simple issue-driven prompting. The system isn't merely reading a ticket and generating a quick response. Instead, it is actively coordinating and running complex executions inside these persistent, issue-oriented environments. Let's look at another defining feature of work system orchestration: making workflow and state explicit. Normally, we might rely on an AI agent to implicitly remember or infer what stage of a process it is in. But in orchestration, the surrounding system takes over that job by tracking work states directly. Imagine a piece of work moving through clear defined stages. It might start as new, transition to in progress, and eventually become complete. Along the way, it could be marked as blocked, needs review, or ready to land. While the specific names for these stages will naturally vary from project to project, the core pattern remains exactly the same. The workflow is explicitly modeled as a fundamental part of the system, so why is this explicit state so helpful? First, it dramatically improves visibility. Everyone, whether human or AI, knows exactly where a task stands, which makes coordination much smoother. It also makes the system more resilient. If something goes wrong, knowing the exact state makes it much easier to handle retries or escalate issues to a human manager. Plus, it provides a clear paper trail for auditability and helps the system logically reason about what specific step needs to happen next. Perhaps most importantly, using explicit states means we do not have to rely on a single long continuous session. We no longer have to hope the AI agent can hold all the relevant process knowledge in its memory at once, because the system itself is keeping track of the journey. Let's move on to our next key point: why reviews, retries, and landing changes belong in this layer. A major reason this orchestration layer is so crucial is that real engineering work simply isn't finished just because an AI agent generated some code. We have all seen AI demos that stop right when the model produces its output. But in the real world, that is just the beginning. Think about what happens after code is written. That code still needs to run through tests. It requires review, probably some rework, final approval, and then the actual merge or landing process. On top of that, you have to keep status trackers updated and manage handoffs back and forth between human engineers or other AI agents. Work system orchestration handles all of these complex transitions. It manages everything at the level of the overarching work item, rather than just looking at the tool calls of a single chat session. This is what makes the system truly realistic. It moves us past the magic of a demo and tackles the operational question that actually matters in practice. How does a piece of work move through a process until it is completely, truly done? And importantly, by managing work this way, the system is equipped to handle the inevitable failure paths and retries, not just the perfect, happy paths. Let's explore how work system orchestration relates to the lower layers of our architecture. A common misconception is that moving to a work system model means leaving those foundational layers behind. But that is not the case at all. Work system orchestration does not replace the lower layers. Rather, it fundamentally depends on them. For example, the system still needs a harness. You absolutely still require a local execution environment, complete with the necessary tools, permissions, memory, and validation surfaces to execute tasks safely and effectively. It also might still use context-based orchestration. The harness executing the work can, and often will, rely on specific skills, rules, memory files, or established repository conventions to guide its behavior. External loops are still very much a part of the picture too. A single work item might trigger repeated, fresh iterations of a harness, all managed smoothly under an outer loop. What about managing state? You may still use persistent workspace management. A work item can easily own or reuse a durable, long-term workspace that is managed by another subsystem entirely. And of course, the system may still depend on standard software development kits or protocols. This means the harness doing the heavy lifting can be seamlessly embedded or controlled programmatically, just as you might expect. So if all these lower-level capabilities are still in place, what actually changes? The crucial difference is the focal point. Work system orchestration coordinates all of these powerful elements around a discrete work item, rather than just centering them around a single prompt flow. It takes your existing foundational tools and organizes them to accomplish a specific, meaningful unit of work. Let's turn our attention to OpenAI Symphony. In our source material, Symphony stands out as the absolute closest example of what we call work system orchestration. We aren't highlighting it because it's the only possible way to design a system like this, but rather because it makes this entire category incredibly easy to understand. So, why exactly does Symphony belong in this category? It operates as a long-running service with a few distinct responsibilities. First, it directly reads work from an issue tracker. Once it has an issue, it creates a completely isolated workspace specifically for that task. Then it executes a coding agent session right inside that workspace, and crucially, it provides the observability and control necessary to manage multiple runs happening at the exact same time. This comprehensive end-to-end management is exactly what makes it a strong example of work system orchestration rather than just simple harness orchestration. Looking at Symphony helps us make a really important conceptual leap. It shows us a major shift in how we think about automation. We are moving away from lower-level tasks, things like manually managing individual sessions, constantly tweaking prompts, wrapping harnesses, or writing scripts to force repeated runs. Instead, Symphony pushes us toward a much higher-level perspective. It represents a shift toward managing work directly at the issue tracker level. It is about applying broad workflow policies, coordinating isolated workspaces, and supervising multiple concurrent work items all at once. Because of this massive shift in scope and capability, Symphony sits squarely at the absolute highest layer of the orchestration taxonomy we are exploring in this course. The simplest way to remember the purpose of this work system layer is this. The human operator manages work, not prompts. When we look at lower layers of AI interaction, humans usually spend their time steering the machine directly. You might find yourself constantly tweaking prompts, managing individual chat sessions, triggering specific skills, or guiding small local workflows. At those levels, you are essentially micromanaging the AI. But as we move up to the work system layer, that dynamic shifts entirely. The human operator increasingly interacts by steering the actual business processes. Instead of typing prompts, your focus moves to managing tasks and support tickets. You are setting workflow policies, acting as the final say at review and approval gates, handling unique exceptions, setting project priorities, and making the final landing decisions. The human operator is still incredibly important, but their control surface has changed. You are no longer operating the AI, you are operating the broader workflow. Ultimately, this shift is one of the clearest signs we have that agentic engineering is moving well beyond standard chat-first assistance. We are maturing into a landscape of sophisticated, higher-level operational systems where AI handles the execution and humans handle the management. Let's wrap up with our key takeaway. We have reached the highest layer in our course taxonomy, work system orchestration. Simply put, this is the layer where autonomous work matures. It stops being about isolated single-session chats with an AI. Instead, everything becomes organized around actual work items. What does this look like in practice? In a fully orchestrated work system, tickets or issues become the active units of coordination. Each issue gets its own dedicated workspace, and the workflow state is always explicit, so you always know exactly where a task stands. Furthermore, the system inherently handles the messy realities of real projects. Retries, peer reviews, and successfully landing the final output are all built right into the system. Because of this, our role as humans shifts dramatically. Instead of micromanaging an AI with endless prompt tweaks, we get to step back. We manage the high-level work and handle the complex exceptions, letting the system drive the rest. This shift in perspective is exactly why work system orchestration sits at the very top of our taxonomy. While the earlier orchestration layers we discussed are designed to help an individual agent work better, work system orchestration does something much bigger. It helps a system manage the work itself. It carries tasks across time through different states and environments and across multiple executions, bridging the gap between AI capabilities and true automated productivity.